So yeah, thank you for the introduction, Dylan, and thank you all for having me. I'm really excited to talk to you all a little bit today about the geology of Henry Cowell Redwood State Park. I've been in Santa Cruz for 6 years now, and this park has been one of my favorite spots. So there's a lot of cool geology in the area. I'm excited. I think we'll have a good time talking about it. Okay. There we go. Okay, so first, a little summary about what we'll be talking about tonight. The talk is in 3 parts. So I will start off with geologic history from a global scale all the way down to the park scale. I'll then go over the rocks you'll see at Henry Cowell State Park, and I will finish with some observations themselves. So also, as Dylan had mentioned, after each one of these parts, I'll stop and take questions. That way it'll give everyone the chance to ask questions specifically about each part, not forget your questions or anything like that. So without further ado, I will start with part 1, and that is the geologic history of the area. And this is going from a global to a park scale. And the reason I'm doing this is because geology is an observational science, right? The easiest way to learn about geology is to go out and observe it. But it's really hard to do that if you don't have some background information about the history of the Earth and the area that you're looking at. So I'm going to start at the beginning, and that is the beginning of the Earth. And bear with me here, but I really think that starting out like big and going small will be helpful. So the Earth starts as a molten ball of lava. We call this the magma ocean. This is just saying when Earth began 4.5 billion years ago, it started as a molten ball of lava. And as we started to cool the Earth, the first solids formed as it's cooling, and these solids are minerals, like you think of them, and they started to condense and float and differentiate. Basically, the heaviest minerals floated to the bottom or sunk to the bottom, and it differentiated by density. And so this gives us our Earth structure. So folks might have seen this, but if you haven't, the Earth is not one homogeneous, one uniform ball. It is made up of different parts. And those parts, as I mentioned, are separated by density, with the inner core being metal, solid metal, the outer core being liquid metal, the mantle being rock, but acting a little bit more like a fluid. And then the crust is our brittle outer shell. And so on the left here, you could see each of these layers. But on the right, this is actually to scale. So you can see that the mantle, the yellow and orange, is the largest part, and the crust is just this really, really tiny outer rim. But what we're going to be talking about is just the crust, just this little part of the Earth. And that's because it's really the only thing we can actually observe. So again, we are talking about the crust now. And the crust is also not a uniform, just solid rim. It is broken up into plates. You could think of these as puzzle pieces. So here's a schematic diagram on the right for what this might look like. You have the crust, and each of these crustal pieces are broken up into a plate. And this gives rise to plate tectonics, how the crust of the Earth evolves over time. So this map I'm showing here on the left are each of those plates. And you'll notice that on some of the plates, there's a continent. On some of the plates, it's just ocean. And these plates are constantly moving over time. So you could see this movie here on the right. This is showing on geologic timescales how these plates might move. So during the course of the Earth, you've been moving these plates around, and you've been crashing the continents into each other because of this plate motion. Way up. I also mentioned that some of those plates have continental crust, some of them have oceanic crust. And this is an important distinction because the type of crust is actually different between the continents and the oceans. The continents are usually thicker and they're more buoyant, they're less dense, they weigh less, so they float on top. Whereas the oceanic crust is more dense, and so it's deeper, it sinks a little bit deeper on the surface of the Earth. There's also, oh, sorry, I forgot to mention something. Really, the important stuff about geology happens at the boundaries of these plates. And that's because when you converge those boundaries in on each other, it really changes the surface of the Earth. So I wanted to mention about what happens at the edges of the plates. And geologists like to bin these in 3 different types. One is a convergent boundary. That's what happens when plates crash into each other, they converge. One is a divergent boundary. That's what happens when plates move away from each other, they diverge. And the third is a transform boundary, and that's what happens when they move past each other. And so what the edges of those plates will look like, what the geology along those edges will look like, will depend on which 3 of these types of boundaries we're looking at. Okay, so now we're starting to talk a little bit more about the plate boundaries. And I know this is a lot, but we'll get to California just right quick. But this is the type of plate boundary that is that was found on the edge of California. So California used to be a convergent plate boundary. And I'll talk to you about the timing of that in a second, but let's talk about convergent plate boundaries for a second. So again, we're at the edge of a tectonic plate, and the 2 tectonic plates are moving towards each other. This is what's called a convergent boundary. And what happened at the edge of California is that you moved together a oceanic plate and a continental plate. And as I'd mentioned, the oceanic plate is denser, the continental plate is thicker and less dense. And so when you converge an oceanic plate with a continental plate, you get what's called a subduction zone. So this little movie here on the right is showing you what a subduction zone looks like. This is when an oceanic plate dives underneath a continental plate. So in terms of California, you could think of California was built during one of these convergent boundaries with a subduction zone. And in this subduction zone, you are making a bunch of volcanoes on the edges. This is why the edge of California is so volcanically active. And that's because this subduction of this oceanic slab causes a lot of melting at the base, causes those rocks to melt at the base of the crust. That lava, or that magma, because it's in the interior of the ocean or of the continent, is buoyant, it goes to the surface, and it makes magma chambers and volcanoes. Okay, so let's bring this back to California for a second. Now, this movie I'm going to show on the left is a schematic diagram. It's a cartoon, but it shows what's happening over the past 40 million years. So this is a lot of time we're going back here. But as I said, California is being built during one of these subduction zones. So we're starting off again 40 million years ago. And what's happening is you are subducting this plate called the Farallon plate underneath the edge of the North American plate. So the Farallon plate is the ocean, that's oceanic crust, and the North American plate is our continental crust. Here is what California would have looked like. So it's kind of scrunched up, you're building it out. And so let's look what happens. I'm going to play this movie. So you're subducting the Farallon plate, and you can see that there's motion. I'm going to pause it. There's motion of the Farallon plate towards and underneath the North American plate, but the Pacific plate, which is on the other side, is moving up and to the left. And this boundary in red is actually the boundary between 2 other plates. So now we're converting basically 3 plates into each other. We have that Farallon plate, the Pacific plate, and the North American plate. And so what happens at about 20 million years, I'm going to pause this. So again, we are subducting that Farallon plate. You're building out California by that subduction zone. So this is the convergent boundary. I'll talk about what happens at the most recent 20 million years in a second, but suffice it to say that over the last 150 million years, this process has been occurring. So between 150 million years and about 20 million years ago, you had this subduction zone on the edge of the North American plate, where you were diving that oceanic plate beneath the North American plate. And so this is a good time to think about this, because a lot of the rocks that you'll see in the park are as old as this subduction zone. So to say that again, a lot of the rocks that you're going to find in the park are remnants of this subduction zone, which is no longer there. So some of the rocks that we'll look at are really, really old metamorphic rocks, and I'll get into what those look like. But this is another chance to look at what that subduction zone would look like. So you have that oceanic crust subducting beneath the continental crust. Here's our California. We have that volcanism happening, and we have a big bowl at the front of it called a basin, and we're going to fill that with sediments. So you have this continental crust, you've got a lot of volcanism, you've got this bowl at the edge, it's filling with sediments, and it's just subducting over 100 million years. But something happens 20 million years ago. You stop subducting, 20 million years ago. Let's look. So we're subducting, it's been subducting for 100 million years. But then you subduct the edge of that plate, and all of a sudden, there's no more plate to subduct. And instead, all of the motion that's going up and to the left becomes dominant. So let's look at that again. We're subducting. We have this Pacific plate moving up and to the left. But then after you subduct the rest of that Farallon slab, all you have left is the Pacific plate moving up and to the left. And that gives rise to our San Andreas fault. So again, I'll play it again, but because you have no more plate to subduct, you're subducting the edge of that oceanic plate, you turn off the convergence. And instead you change to a transform boundary where the crust is moving past, the two plates are moving past one another. Okay, so this gives rise to what we all know today as the edge of the Antarctic, or of the North American plate, and that is the San Andreas fault. That is a transform boundary. So the North American plate is now moving down and to the left, and the Pacific plate is moving up and to the left. The North American plate down and to the right. Okay, so now this is a transform boundary. So this transform motion gives rise to our coastal ranges. So the coastal ranges are mountain ranges. Here's a map of California again, and the coastal ranges go from the north all the way down. Here's Santa Cruz here. Here's the park up in here. This is our Santa Cruz Mountains. And the coastal ranges go all the way down. The San Andreas Fault bends. This is where we have the transverse ranges, and then we have the peninsular ranges all the way to the south. But again, this is one long mountain chain on the coast. And this is a result of that San Andreas Fault motion. Okay, so I'm going to play one more movie for you. This is a little bit more complicated, but I just want to point out the motion that causes those coastal ranges. So again, this is going from 36 million years ago to the present. And you can see at 20 million years, you start to move everything up and to the left. That's when you stopped subduction. And all of the plate motion that is up here, and in this red part, are the coastal ranges. So I'm going to trace it with my cursor. This is where the coastal ranges are. Here's the transverse ranges, and here's down in the peninsular ranges. So if I play that again, you can see that at about 20 million years ago, when we get to 20, we're going to start our San Andreas Fault, and motion is going to start in this area at about 10 million years, and now we're going to make our coastal ranges, and that's with motion along this part of the fault. So these transverse ranges, these coastal ranges, are a result of our San Andreas Fault motion. And that just is driven by uplift. So when you move these pieces of the faults past each other, they cause uplift of the coastal ranges. So to take a closer look now, we're going to bring this into park view. We still have San Andreas Fault motion to this day. It's still a transform boundary, as you can see. And if we zoom in, what we see is the San Andreas Fault isn't just one fault line. It's actually a big group of faults called a fault zone. And the park falls right within that fault zone. We have the San Andreas here in red. We have the Zayante Fault, which is kind of not exactly parallel to the San Andreas. Then we have a bunch of these faults coming out through here, offshore of Santa Cruz. And then there's one fault that cuts through the park itself. That is the Ben Lomond Fault. So the Ben Lomond Fault cuts through the park itself. And if you're following along with the slides I shared before this, I shared a couple of extra slides about faults that will give you a little background information. But in the case of time, I will just go with what I've told you, and that is faults are these areas where you are moving plates past each other, and we have our fault motion that's driving our uplift of the mountains that make the park, and we have the Ben Lomond Fault that's cutting through the park. Okay, so that is the end of part one. That's just some geologic background to get us all thinking about how the rocks were formed and what they went through to make the park. I'll talk you through each of the rocks as we go that you'll find at the park, but that was just our background. Does anybody have any questions on the background? This is a time that you can all raise your hands or put something in the chat. I want to make sure I don't throw too much at you, and I allow you to ask some clarifying questions if anything was not clear. Does anybody have questions? I see one raised hand. Let's see.
Yeah, Gary, you have a question. Go ahead.
Yeah, I just wondered if you could provide the link to those slides. I got in a little late and I missed that.
Hey, Gary, yeah, direct your attention to the chat box at the conclusion of our session this evening. That's when I will be uploading the slides. Those folks who show up a little bit later can't access them. So yeah, we'll drop them in the chat box at the end.
Okay, thanks.
Anybody else have any questions? Was there anything that wasn't clear? I know I threw a lot at you. Anything that's not clear about the background geology, the subduction zone or the transform boundary? Everybody good? Oh, yes. Okay. I have a question in the chat from Emily that says, what do you mean by transform boundary? Let me go back because I think I went over that a little bit quickly. So I'm going to show this. So this is just a graphic. I'll show you a better image of this in a second. But again, the edges of these plates, the edges of the tectonic plates come in basically three main types. The three types are convergent. So you could think of that as when you crash plates directly into each other, you converge them. The second type is divergent. That means that you move plates away from each other. And the third image, or the third type, is a transform boundary. And that's when you're moving plates past each other. You're not moving them towards or away, but you're moving them side to side. And so if we look at that in map view, let me just find a map. So convergent is where you get our subduction zones. That's what it looked like at the beginning, or 150 to 20 million years ago. And then at 20 million years, you start your San Andreas faulting. And that is where you have the plates moving past each other. And by past each other, I mean up and to the left and down and to the right. Oh, yes. Okay. Thank you, Emily. Strike slip is the same thing as transform. Transform's kind of like the old school definition, or the old school way of mentioning it. But yeah, strike slip is the same as transform. Thank you for that clarification. I see what causes uplift at a transform boundary. That's a very, very good question. And I was going to put a diagram to show you this, but in the interest of time, I cut it out. So sorry about that. But what you could think of it is there's two reasons why you get uplift along a transform boundary. One is that when you're moving the plates past each other, it's not a perfectly smooth surface like this shows over here. It is very rough, and there's a lot of nick points where you're moving, and then you like kind of stop the motion. The motion kind of gets stuck. There's also bends. It's not a perfectly linear edge boundary. There's bends in it. And when you hit those bends or those nick points, some of the motion past each other actually changes to like minor areas of uplift. But over time, remember, this has had 20 million years to uplift. You actually get a lot of uplift. Not as much as what would happen in a convergent plate boundary, but you do get linear mountains. So if that definition didn't really help it, sometimes pictures are easier. I could say after and show you a picture if you're really interested. But yeah, it's really about the bends and about the fact that a lot of times, even though the plates are moving past each other, when they get stuck, they get pushed up. The motion kind of like wants to kind of curl over itself and push up. So yeah, that's why you get uplift in a transform boundary. I have one question. I think I'm doing all right on time. I'll take one more and then I will keep going. And that is, what is the age difference between the Coast Ranges and the Sierra Nevada? The Sierra Nevada are predominantly 250 million year old rocks. The coastal ranges, the rocks are everywhere from 150 million years old to like a couple of million years old. So generally the coastal ranges are younger rocks. The uplift of the range, though, happened only starting at about 10 million years ago. So the rocks themselves are, about 100 million years apart, but the actual tectonic motion is, about 240 million years apart. But we'll get into that a little bit more when we talk about the rocks themselves. So great questions. I will keep going. I will get into part 2. Now let's get our hands dirty a little bit. Let's actually go and look at the rocks in the park. These aren't my observations, but I'm going to take you through how the rocks formed. I'm starting off with a picture of a place you all probably know. These are the sand hills. So this is a type of rock we're going to see. Some may argue the most spectacular. Before I go into the rock types, though, I'm going to be using these two terms, and I wanted to make sure that I introduce them. So I'm going to be talking about bedrock. Bedrock is simply the solid rock base upon which everything else sits. So bedrock is our rock base that we're standing on, but oftentimes you also see areas where you have boulders or sediments. Those boulders and the sediments are not bedrock. And I'll show some pictures that shows you that could be actually a little bit tricky. Sometimes it's hard to see what's bedrock and what's not, but bedrock is actually the rock base. It's not a broken piece, it's the rock base. And then an outcrop, you'll hear me say the word outcrop a couple of times in this talk, and that is areas where the bedrock is exposed. So not every place the bedrock is exposed. And actually, if you go walking in the woods, oftentimes all you see is trees. You don't see any bedrock. All you see is trees and boulders. And so we want to look for outcrops. We want to look for places that we're actually seeing the bedrock. And so when I say bedrock and outcrop, that's what I mean. Okay, so let's talk about the deep rocks beneath the park. These aren't necessarily rocks that you will see a lot of, but every once in a while, you'll see like a granitic rock or some really tiny pieces of granite. And that's because the bedrock below the park is this piece of the crust called the Selenian block. That is the Selenian block. So if I look in map view now, this is a map of just some of the rocks in California. You have your Great Valley, you have your Selenian block in green. Some of the granitic portions of the Selenian block are in red, and then you have the Sierra Nevadas in orange. And the Selenian block rocks, you can't really see, as I said, you can't really see a lot of them in the park. They're kind of below the park. But if you go down to Point Reyes, all those granitic rocks that you see down there, those are the Selenian block. So you might be asking, well, if you can't see in the park, why are you bringing it up? And the reason is it's actually pretty important for all of Santa Cruz, because again, it's the bedrock below Santa Cruz. And oftentimes I used to walk around the beaches of Santa Cruz and wondered why I picked up rocks that looked like perfectly good Sierran granites. Like I just went to Yosemite National Park and I picked up a granite. And the reason is, I'm just going to show this graphic one more time. And I want you to pay attention to what happens. This is proto-Santa Cruz. 40 million years, Santa Cruz was the coastal rocks that make up Santa Cruz were down by Arizona. And as you march through time, you start to create your transform boundary and move all of these rocks. These rocks are going, this big block of rocks here that makes the coastal rocks of Santa Cruz today is going to travel all the way up north from Arizona all the way to where it is today. And this is the Selenian block, this little tiny block of rocks here. Okay, so it's actually really cool that someone asked about Sierra Nevada granites, because some of the granites that you could find in areas of Santa Cruz are remnants of Sierra Nevada granites, but these are the rocks that are really, really deep below the park and aren't really making up what we can actually observe in the coastal ranges today. But the deep basement rocks are actually very, very similar to the Sierra Nevadas because they used to be down here. So that's the Selenian block. Now let's talk about the rocks that can be found in the park. And I'm going to be referencing this psychedelic looking map here. This is a geologic map. And without a key, it's kind of useless. So I'm going to take you through it with a key. But what you can see is a bunch of different colors. Each different color on this map is a different type of rock that is at the surface at that area. So let's get ourselves oriented here. Here's Santa Cruz. Here's our Monterey Bay, part of the Monterey Bay at least. Here's our San Lorenzo. This is the University of California, Santa Cruz campus, this big purple blob. And Henry Cowell Redwood State Park starts out up here, up in the mountains. This dark black line, if you can see it, that's the Ben Lomond Fault. So you can see, as I said, it cuts right through the Henry Cowell Redwood State Park. Okay, so we have a bunch of different rocks that we see in this park. It's actually spectacular how many different rocks outcrop here. You don't ordinarily see places like this if you went to like the middle of the country, but because we're in such an active tectonic zone, because we're at the edge of the plate, you get a lot of different rocks that are outcropping at the surface. So let's march through each of these rock types. So I'm going to start off with some of the oldest bedrock you can see at the park. So the oldest bedrock you can see is between 200 and 130 million years old. And these are predominantly these pinks and these reds. So I'm going to be talking about these 4 rock types. I'm going to be marching you through each of them, but it's the pinks and the reds that we're looking at. These are our old bedrock. And as I said, a lot of this old bedrock is going to start out in the subduction zone, because if you recall, the transform boundary only happened 20 million years ago. So if these rocks are 200 to 130 million years old, they must be forming in the subduction zone. And that is going to be the case. And it's really, really an important factor in why they look the way they do. Okay, so without further ado, let's look at our first rock type, and that is diorite. That is diorite. It's specifically a quartz diorite. That's why on this map it says QD. It's these pink rocks up in here. And so as you can see, the park is up here, and you can see that most of the park is made up of this quartz diorite. And what this quartz diorite looks like, it kind of looks like cookies and cream. I always call it a cookies and cream rock, because it's predominantly made up of dark minerals and light minerals. So remember, rocks are made up of minerals. Minerals are the building blocks of rocks. They're the pure pieces that make up the rocks. And so you have minerals that are dark and minerals that are light that make up your quartz diorite. And quartz diorite is an igneous rock. That means it's forming from the crystallization of lava or magma. And it's forming, this quartz diorite is forming about 130 million years ago. And it's forming in the part of the subduction zone that's melting, and this big magma chamber that's sort of in the interior of that subduction zone, inboard, that is, of the coast itself. It's forming by solidified magma. And the reason it is at the surface today is because it's been uplifted and all of the rocks above it were eroded away. So as you change the coast of California over time, over the past 130 million years ago, this magma chamber that had formed would have solidified, would have uplifted, and everything that was above it would have just been eroded away. So it was exposed by erosion, but it was not metamorphosed. And I'll get into what that means in a second. But again, this is an igneous rock. And if you look, as I said, this makes up a lot of what we see in the park, but it doesn't, most often when you find it in the park, it doesn't look like this beautiful piece that is cookies and cream. It looks really, really weathered. So I'll get into what that means in a second, but it'll look red. It'll look red instead of a pure white and dark. And so this is a piece of a weathered piece of quartz diorite. And you can see that the outside where it was exposed to the elements is red. Whereas if you broke off a fresh surface, it might look something like this. It's more creamy colored. And moderate between the two, you get just a little bit orange going towards this highly weathered. So when I say weathered, what do I mean? Weathering, and this is specifically called chemical weathering. I won't get into the distinction, but this is weathering, is when you have a chemical reaction that changes the minerals. So these chemical reactions most often happen when you expose the rocks to water. If you've all been up to the park, you know it's a very wet place a lot of the time. When you expose the rocks to water, a chemical reaction changes the dark parts into rust. So you add oxygen to these dark minerals and they rust, just like any rust may happen in your kitchen if you're not careful, or in your house if you're not careful. So the quartz diorites that you're going to find in the park are going to look more like this red surface. And I'll show you some pictures at the end to show you how that might look like in place. But suffice it to say, if you find this igneous rock, it'll probably be pretty weathered and it'll be highly red because all of these minerals have rusted away. Okay, let's talk about the next type of old bedrock. This is slightly younger than the quartz diorite. This is called schist and quartzite. So you can find these on the map in this purple color. So predominantly the rocks that are on Santa Cruz campus are the schist and the quartzite. And you can also see up in the hills, kind of, what is that, north of the park, you also have some of the schist outcropping and some of the quartzite outcropping. I'll get into what those rocks actually are in a second, but these are the next two rocks you could find in the park. You'll see that in the actual park itself, you don't see much of this purple color, but if you go looking in the rivers and stuff, you'll find some of these rock types, the schist and the quartzite. So these rocks were deposited at between 150 and 120 million years ago, which means they're also being deposited in the subduction zone, but they are much different than the diorite. I mentioned that the diorite was this cooling magma. These samples actually started off at the front, on the edge of the continent. I mentioned that on the edge of the continent in a subduction zone, you get a big bowl. We call this a basin or a trench. And in this big bowl, you sort of collect all of the sediments that are coming off of your mountains. And you collect those sediments. They look a lot like sediments today, but they have 120 million years to interact with this subduction zone. And what happens is they get buried in the subduction zone, kind of shallow, not all the way down, but sort of in the shallow parts of the subduction zone. And when you bury them, when you bury those sediments that were right in this area, they get really, really hot and they get very highly pressurized. And when you take sediments or any rock on the surface and you bury it and you expose it to heat and pressure, that changes the rock in a process called metamorphism. That's your second rock type for those familiar. So these are two metamorphic rocks. And so let's get into how they actually form. So schist generally forms when you have a sedimentary rock, not always, but generally starts as a sedimentary rock. And then, so a sedimentary rock that might form that is mudstone. So here's a piece of mudstone. And that mudstone is heated and pressurized, and it's metamorphosed. And one really, really special part of schist, you might be able to see this in this picture here, is that you get a really, really shiny edge on a schist, a shiny surface on the schist. That shiny surface kind of looks scaly or sometimes smooth. That shiny surface is something called foliation, and it's very, very specific to metamorphic rocks. And so I'm going to describe to you what foliation is. So say we start off with this mudstone here, and it has a randomly oriented minerals. It's just all tiny pieces of different types of minerals and very, very small sediments that made up the rock itself. But then you start squishing it. Remember, heat and pressure, you squish it, and all those randomly oriented minerals start to line up in the rock. And so when you go from a mudstone to a schist, you get all of those minerals lining up. That lineation, those lines, are called foliation, as I mentioned. And so one of the really distinguishing process or properties of schist is that foliation. You get that shiny surface because all of the minerals are lined up like they're sitting on a table, and their broad faces are pointing out at you, and the light glints off of them. All of those lined up minerals on the surface of schist, they reflect the light out at you, and it looks shiny and scaly. So that's schist. It's very distinctive if you find it in the park. I also mentioned another metamorphic old rock that is quartzite. That forms over a very, very similar process to schist. You take sediments and you heat them and pressurize them, so it's a metamorphic rock. The distinguishing factor between whether a rock becomes a schist or a quartzite is just what the sediments are when you start off. So as I had mentioned, mudstones turn into schist most often, but if you have a sandstone, say, that's high in the mineral quartz, you'll make a quartzite. That doesn't have foliations because it doesn't have the same types of minerals as a schist. Really, the dominant feature of a quartzite is that it's recrystallized. So it looks sort of like one sort of matte surface with tiny, tiny little crystals, like you can see here on the right. And so you can't see any of the sand grains in a quartzite anymore. You might not even realize that it used to be a sandstone because all of those little sand grains were recrystallized. And oftentimes the ones you can find in the park are these beautiful pink and purple colors, but it's sort of a nondescript rock type, so it sometimes can be hard to find. So those are our schists and our quartzites. Now, the final rock that you can find in the park that is old and was formed in the subduction zone is marble. Now you might be saying, well, Gavin, it looks like the park is up here in this map and you don't have any marble mapped here. But I will assure you that if you go around the park, you can find pieces of this marble. And we'll get into that in a second. But sort of the best place in Santa Cruz to find the marble is on Santa Cruz campus. There's actually quarries where they were quarrying out the marble. And so on this map, you can see it as this brown splotch, but again, you can find it in the park, and we'll talk about that a bit later. So what about this marble? It's actually the oldest rock in the park. It was deposited as shallow ocean sediments about 150 million years ago. And so this is part of the subduction zone, but it's not anywhere near the subduction zone like the schist or the quartzite or the diorite. This is actually forming all the way out in the ocean, in the shallow ocean. But again, this is a metamorphic rock and it was uplifted during plate motion. So that's why it's here. But really, to understand it, let's dive deep into marble. What is marble actually? So marble is a metamorphic rock. That means it started off as one rock and then was heated and pressurized and changed into a different rock, changed into marble. So you make marble by starting off with limestone. And limestone is this very special rock. It's actually, geologists call it a biogenic rock because it is formed by organisms that were living. So over here on the right, I'm going to take you through how that happens. How do you make a rock out of living organisms? Well, in shallow ocean environments, you get these little tiny plankton, like I'm showing here. These are sort of microscopic creatures, and they take some of the nutrients out of the ocean water, and they make their shells out of that ocean water, and their shells are pretty much rock. They're pretty much made out of rocks or minerals. And these organisms are some of the most abundant organisms on the surface of the earth. So you can see that here's an example in the modern times of a bloom of these plankton, and you can see them from space. This is a planktonic bloom as seen from space. And you can see it's almost ocean wide, these little microscopic organisms. And what happens is these organisms live, they die, and their shells are deposited at the base of the ocean, on the bottom of the ocean. And you get so many of them piled up on the bottom of the ocean that you can get tens to 100-meter sections, tens of 100-meter to 100-meter packages of limestone. Limestone that looks like this. It's this very, very sort of nondescript grayish rock, but it's made up of microscopic organisms. And if you're lucky, sometimes you can find some remnants of those organisms in the limestone. So getting back to our marble, it would have started out on the edge of the subduction zone as those minerals that were making their shells and dying, and they would have deposited their shells on the base of the ocean, on the ocean floor. Then that limestone was brought down in the subduction zone. It was heated and pressurized, and it makes our marble. So that's how we get marble in this area of the world. And that is why we have marble in the Santa Cruz Mountains today. Okay, so those were our old rocks, our rocks that were forming in the subduction zone, but we don't have all rocks that were forming in the subduction zone. We have much younger rocks in the park as well. And that's kind of an interesting thing. We have, in this one area of the world, we have rocks that are 150 million years apart in terms of when they were formed. So the less than 30 million year rocks are going to be sedimentary rocks, and they're going to be dominantly sandstones and mudstones. And if we follow along on the map, these are our yellows. And you can see there's little tiny lenses of these all around this area, but you can see them mostly over here on the south side of this map. So again, sandstone and mudstone. Let's talk about where they form and why. So less than 30 million years ago, you no longer have a subduction zone. Now the coast of Santa Cruz looks somewhat similar to what it might have looked like, what it looks like now. So 30 million years ago 20 to 30 million years ago looks somewhat similar to what it looks like now, where you have beaches and you have shallow water happening. So I'm gonna show this little schematic that just reminds us where we're at. We have deep ocean deposits, which are forming our mudstones, and shallow ocean deposits, which are forming our sandstones. Kind of makes sense if you think about it. Like, what do you have along the coast? You have beaches, those are made of sand. So beach deposits are normally sandstones. Whereas if you go out to the middle of the ocean, a mile out, say, there's no more sand. You have only muds at the base of the ocean there. And so that's where you get your mudstones. So let's talk about the mudstones and sandstones in the park. So the sandstone that we find, this is one of our most iconic rocks in the park. That is the Santa Margarita sandstone. The Santa Margarita sandstone. So it's a very, very white sandstone. It was deposited as a beach deposit 10 to 12 million years ago. And it was uplifted when the San Andreas Fault motion happened, but it was not metamorphosed. So this is a sedimentary rock. And again, sometimes you could find really, really beautiful fossils in it. I'll get into that in a second. But that is our Santa Margarita sandstone. It's much, much younger than the old metamorphic rocks we'd find in the park. The Santa Margarita sandstone is very, very well preserved. That's why it's so white. And it has a diverse range of fossils. So many of you have probably walked around the sandhills in the park, and that's where you could find sand dollars, you could find shark teeth. Some of the most iconic are the old mammals. There were a bunch of big mammals that were around at that time. And after it formed 10 to 12 million years ago, The Santa Margarita sandstone would have been buried by some of the younger formations, some of the younger sedimentary rocks we have in Santa Cruz. And eventually, because of the uplift of the mountains, all of these rocks above it would have been eroded away. And that's why we have outcrops of it today. The other sedimentary unit we have in the park is called the Monterey Formation. So the Monterey Formation are these blues and greens. The Monterey Formation is also sandstone and mudstone. It's older though. So it's 12 to 17 million years old instead of 10 to 12 for the Santa Margarita. And the Monterey Formation is not as beautifully white as the Santa Margarita. It's got a lot of mud in it. But process-wise, it was formed pretty similarly. It's a sedimentary rock and it was uplifted by the San Andreas Fault, but not metamorphosed. So it is sedimentary rock, as I mentioned. And what makes the Monterey Formation sort of distinctive is that it's an oil-bearing formation. So you really can't see it in a lot of places up north where Santa Cruz is. It only really outcrops in the mountains because you've had so much erosion that you've eroded off all of the rocks above it and you've kind of brought it to the surface. But really, if you wanted to see the Monterey Formation, go to Monterey or down south and along the coast. And this is actually the formation that holds all of the oil that LA is famous for having. So all of the oil derricks you see on your way down to LA, those are digging into the Monterey Formation. But you could just find some small lenses of this Monterey Formation in the park. And again, the reason it's there is because these rocks were uplifted during the uplift of the mountains, and all of the rocks above it were eroded off the top. Okay, so those are our rocks, and I'm gonna end the talk by just giving you some pictures to get you oriented with, if you're walking through the park, what will this all look like? What will these rocks look like? So I'm at about 47 minutes, so I'm getting close to time. Part 3 is pretty short though. So if anybody has any questions about the rocks I just talked about, all the rocks you can actually find in the park before we go to our geologic observations, you can ask them now. Either raise your hand or maybe put it in the chat. I see Emily with a raised hand. I see a couple of raised hands. Go ahead, whoever wants to go.
Okay, so I have a question about the depositional environment of the stuff that got metamorphosed into the schist and the sandstone.
Totally.
So it got, it was like laid down in the ocean, and then that plate was kind of just like a conveyor belt into the subduction zone, and that's where they got metamorphosed.
That's exactly right. Yeah, thanks for that analogy. I should remember that. It's exactly like a conveyor belt, right? So here's your crust, your oceanic crust. The sediments were kind of deposited in this little trench here. And just like a conveyor belt, you're moving the sediment down in the subduction zone. And as soon as they're put inside the subduction zone, it's really, really hot. It's really highly pressurized, and that's where the metamorphism happened. And so because they were buried, in order for them to be on the surface now, that means this area must have been really, really highly uplifted, and there must have been a lot of rocks above them that were eroded away to expose that shallow part of the subduction zone. But that's exactly right. Good question. Does that make sense?
Yeah, thank you so much.
Perfect. I saw one other raised hand. Does anybody else have a question? No? All good? Okay, there'll be time at the end as well. Let's go to some park observations. Because really, it's not like you're walking around and it's as easy as looking at a map. And it turns out that finding rocks in the park could be really, really hard. So I took a few pictures on the last time I was at the park, and I'm going to give you a few examples of what this might look like. So again, just a reminder, bedrock, the solid rock at the base upon which everything sits. Outcrop are areas of exposed bedrock, not boulders. Okay, so if we find boulders in the park, you can assume that they've come from elsewhere, but that's okay. But really what geologists love to find is an outcrop, because that tells you really what on a larger scale the rocks are like at the base that you're standing on. Okay, so let's start with the sandhills. Those are, again, arguably the most iconic and some of the easiest to understand. So y'all probably know more about park geography than me, and maybe have explored more of the park than I have, but I found the best place to find the sandhills are kind of near the campground. So if you go walking near the campground, you'll see sandhills that look like this. And this is a world-class sandstone outcrop. This is like more beautiful and more pure and has better fossils than a lot of the sandstones that you'll find anywhere else in the world. So in terms of actually understanding the rocks, this is sort of an easy place because you have such uniform rocks that are outcropping at the surface, and you don't have to look hard. And the reason that you don't have to look hard is sort of interesting. So what do I mean when I say you don't have to look hard? Well, I mean that there's not a bunch of vegetation covering the sandstones. You have these really nice, beautiful exposed outcrops, which is not the case in the really tree dense areas of the park. And so it's kind of interesting if we think why the vegetation in this part of the park has much less tree cover. And I will say that I'm not a botanist. I'm not really a plant person, but what I know about sandstone is that it is very low in minerals that provide nutrients to plants. And so it's not really easy to get big forests on the top of sandstone because you don't have minerals that can weather away and provide these really soil dense areas where you can grow really, really dense forests on top of. So while you do have some vegetation on the sandstones, you will very seldom find really dense forests on the sandstone like you would find elsewhere in the park. So it's kind of cool. The bedrock in this area is controlling the vegetation. But what about the other parts of the park? Being a geologist is not always as easy as walking around to the sand hills and just looking at beautiful sandstones. This is what the park might look like if you're walking through it. This is from a hike I went on just the other day at Fall Creek. Sorry for the dark photos. It was getting late. I was battling to get around the park before the sunset. But I want to ask everybody a question, and this is rhetorical. You don't have to answer me, but does anybody see where outcrops might be on these photos? Is there an outcrop at all? Here's a path through Fall Creek. Here's a part of the creek itself. And I'm actually going to tell you that there are outcrops in this part of the park, but they're just really, really hard to see. With the naked eye, you might not even know they're there unless you're really looking for them. And so I'm just circling the areas of exposed bedrock. So this part of the ledge here to the left of the path is actually pretty pure bedrock. But the reason it's so dark is because of that weathering I talked about when we talked about diorite. So these are both outcrops of that diorite, but without really pulling a piece off and looking at it and maybe breaking it to see a fresh face, you might not even know it's there. But if you are lucky enough to find an area where these rocks are breaking or a fresh surface, you can see that some of this diorite is outcropping in the Fall Creek unit. But as I mentioned, yeah, most of them, even if you find a piece that's broken off, most of them will be very, very highly weathered. But not all is lost. If you really want to find the rocks, go to the river, go to the San Lorenzo, because oftentimes what geologists want to look for is fresh rocks. That means surfaces that aren't weathered. And rivers are really good at transporting rocks with fresh surfaces. So you could find fresher outcrops along the river. They're sometimes covered by vegetation like this one, but they're there. But also, if you just want to get a sense and look for the rocks that we've talked about in this talk, just go along and walk along the river and you'll see little tiny cobbles. And those are going to be pretty consistent with all of the rocks that we talked about tonight, all the rocks in the surrounding vicinity. Every once in a while, you'll get a rock that came from really far away, but not really that often. Most of the time, all of these boulders will be the rocks that we talked about, the rock types that we talked about in this talk. So check the rivers. Okay, this was sort of a conundrum I had when I was walking through Fall Creek, and that was, okay, I know there's a kiln at the end of Fall Creek, right? That's the famous loop that you go to. You go up, you find this now kind of overgrown kiln. And what did they do at kilns? Kilns were there because they wanted to take marble that they had quarried, and they wanted to get it really hot by making fires, and they wanted to take that hot marble and make lime. So lime is sort of a byproduct of when you heat marble, and lime is a very important component of concrete. So they had the Davenport cement factory just up north, and they made all of the lime for all of that cement in these kilns that are all around Santa Cruz. I know that a lot of you are probably familiar with this story, but me as a geologist was thinking, well, there isn't any marble that's mapped in this area. And so why was the kiln here? Were they really just like bringing marble to this area deep in the woods? That doesn't seem like a very good business model. But sure enough, if you walk around this area in Fall Creek, you do indeed see a really, really high density of really white rocks. Again, these are really weathered, so you might not even realize that they're marble. But you find mostly boulders of this marble, so it's possible that this is transported, but based on the really high density of marble you see in this area, and you can also see things that I think are actually marble bedrock. I think there are little pockets of marble up in Fall Creek unit that you could find, and you could understand what they were quarrying out and putting in these lime kilns. So that's another place to look for some neat, interesting rocks that we talked about, especially as you get up towards this lime kiln. Okay, I will talk a little bit about the thick weathered bedrock. So if you walk along the creek, you will see edges along the path that look like this. They're really, really densely rooted. If you pick them up, they're sort of like sediment. There's maybe actually soil up top of them. This does not look like rock anymore. And this area is very, very highly weathered bedrock. So it's no longer bedrock. It's totally weathered out. It's no longer a rock. It's been broken up into sediments, but it explains why you can have thick tree cover here, because these rocks are easily weathered. And when you can weather rocks, you can bring nutrients to the surface. Those nutrients help form soils when you have vegetation or organic matter in a place for a really long time. And that soil and those weathered rocks are what the trees really, really like. So that explains why you have really dense trees here, but not in other places, not in the sand hills, for instance. Okay, finally, I'm gonna talk a little bit about hydrology. I know you signed up for a geology talk, but I would be remiss if I didn't talk about this really cool hydrologic feature that is in the Fall Creek unit of the park. By hydrology, I mean the study of water, how water moves across the surface. And I'm going to be talking specifically about the waterfall. Sorry for this bad picture. This is a cell phone picture of it. You can't really see, but up near the lime kiln at the end of the loop in the Fall Creek hike, there's this area where there's a little waterfall that's sort of the head of the catchment that is forming the creek down through the park. These are what we call headwaters. And what this is it's a raised spring. This is actually a place where the aquifer is so shallow that it's intersecting with the surface, and you're actually getting groundwater that you could put your finger on the groundwater spring. So if you walk up to this area, and if you go to the lime kiln, you can't miss it. If you walk up to this area and you walk up close to this edge here where you have this little waterfall, you can actually see where the aquifer is being drained out and is effusing its water out onto the surface. And so this is a schematic diagram that was from a different area, but it's really, really a good picture of what's happening here. So we talked all about the uplift in this area. And when you get uplifted areas, you uplift aquifers, these porous sandstones or these porous sedimentary rocks that hold a lot of water. Those are our aquifers. And when the aquifers intersect with the surface, you get these little springs that come out here. And this is just a beautiful, like really, really amazing place to go look at what happens when you get an aquifer that is brought up to the surface and you get the head of a spring here. So it's really a special place. And I really just wanted to put it in there as just something really special about the park. Okay, so with that, That will be the end of my talk. I just wanted to go over a couple of the highlights and open it up to any more questions. I'm at an hour, so sorry for going a little over time. But we talked about how California was built by the subduction zone, which happened about between the time of 150 million years ago and 20 million years. You had this subduction, and a lot of the older rocks in the park that were forming in this area of the subduction zone, and they're either the sediments that were metamorphosed there, or in the case of the diorite, actually a magma chamber that was just sitting there and was uplifted over time. And as you erode the rocks off the top, you expose these metamorphic or igneous rocks. And then at other places in the park, you have much younger rocks sort of that were being formed in the environments that are kind of similar to today, these beach or ocean environments. Those are our mudstones or our Santa Margarita sandstones. And you have a very diverse sort of range of areas in the park where you can go look at these rocks. And it's depending on the rock type, it really kind of dictates what the area looks like. So with that, I will thank you all for your attention. I had a really, really great time talking with you all today. I'll open it up to any questions. I could stay indefinitely to talk to y'all after the talk, but again, thanks for listening.